jetzt müssen wir da Telefonat ist.
Okay, great. So let's get started. So before we talk about the technical stuff, right? So let's talk a little bit more about logistics because we are actually approaching the half of the course. So today we are going to continue to talk about normal forms and the multivital dependency. We won't fully use up the 90 minutes. But if you have any questions, I'll actually be here to answer them, right? So I'll be here, stay like on this Zoom call as long as it will take. And whatever question that you have, just after the technical content of this lecture, just unmute yourself and ask, and I will be here, okay? So, and if you think about this course, right? So essentially we are going to talk about two different things. The first one is how to use a database as a user, right? How to write SQL queries, how to design your database schema, how to behave like a very good user of a database. And the second component will be how to actually construct, how to build the database management system that the user is actually using. So this lecture today is the last lecture of the first segment. Right? This is the last lecture that we are going to have about how to use a database system. So starting from after we are going to talk about how to build up a database systems. So it's also a good time for us to kind of do a review about what we have been doing, right, in the last almost 2 months now, right? So, and on Friday, the next lecture, we are going to have an exam review session, right? So essentially we are going to review, put into structure what we have been learning so far, right? Refresh our memory, right? To really put everything together, right? Because so far we have been learning this in a linear order, right? So it would be great if we take a kind of high level view of what we have been learning and try to refresh our memory. So we are going to do that on Friday, okay? And we are also going to define the scope of the exam, right? So on Friday, because we have been learning a lot of things, especially a lot of theory, right? To make sure you understand fundamentally what we are talking about. But some of them will not be in the exam, right? So we are going to make that precise also on Friday, define the scope of the exam. And we are going to together go through some exam questions in previous years to make sure we have the right expectation about what we are expecting from you.
Wir machen das irgendwie Lautsprecher.
Also, aber dann müssen wir also verkrüppelt darüber schauen.
Yeah. So, and then next Wednesday, right before Easter, we are going to talk about advanced analytics, right? So there are actually those fancy things that you can do inside your database systems. How can you do machine learning inside database? How can you do data mining inside database systems, right? So that things are going to be very useful when you go find a job and do something real, right? But they will not be in the exam, okay? And then it's Easter, and right after Easter, we are going to switch gear and talk about how to build a database system, not how to use one, okay? So this is actually logistics about this week, next week, and also the remaining part of this course. Another thing is, so I think your student representative also talked to you about it. So there's a link that you can provide feedback to us about how we can run this course better, and please do, right? So we are in the process of continuing to understand how to run this course better, especially about the exercise session, right? So that is actually something we really want to improve this semester. Whatever kind of feedback you have about the lecture, about myself, also about the exercise session, about how we could run that better, or please let us know, right? So we will try to reflect your feedback as much as possible this semester. But if you are not able to make some of the changes, we will do that in the next year. Okay. So this is about logistics.
Bro, ja, der Link.
Yeah, can anyone just mute yourself? Let me try to mute all. Okay, great. Sorry. Yeah, I think I muted. So now we continue to talk about the technical stuff that we have. So what are we talking about in the last couple of weeks? The thing that we have been talking about is this kind of relatively simple process that you have this conceptual model, which is your view about what data you have, what the relationship you have among them in the real world. And we try to translate that into a relational model, right? So on one hand, you have this entity relationship diagram about the entity side, about the relationships. On the other hand, you have this beautiful relational model, right? Everything is relation, you have relational schema. How can we translate it, right? Given one application, we talk about how to model it in a conceptual way. And we have spent a couple of lectures now to talk about how to translate that conceptual model into a logical model that you are able to implement inside your database system. And if you look at this process, right? So it's relatively simple. And the way to think about an ER diagram, a conceptual model, is try to think about that as a language introducing constraints, right? For example, you have these three different entity sets with this relationship are connecting all of them. And then the cover is essentially define all those constraints, right? So whenever there are three entities, A, B, and C, participate in this relationship R, they need to say, yeah, A is inside A is inside A, B is inside B, for example, right? And then whenever you have those cardinality constraints, you also have, now we know how to talk about it. Now we have this functional dependency, right? When you have, for example, you have this one here, right? It actually means you have a functional dependency from A, B to C, right? Once you know A, B, you know C, right? And then once you have this one for the B, you have the functional dependency from AC to B, right? AC decide B, right? We talked about that last week, really precisely what we mean by that. But if you look at this conceptual model, right? So it defines nothing else. I mean, it's tell you all the underneath side, all the relationships. Underneath the cover, it can be translated into a whole bunch of logical sentence about what we are expecting in this application. And when we do the translation between the like from this conceptual model to a logical model, what we are doing is actually try to define a database schema, right? That can contain all the can store all the information you have in your application, but also try to enforce as many constraints as possible that you have in this conceptual model. And some of those constraints can be enforced by, for example, primary key, right? If you look at relation R, right, your primary key say, yeah, my primary key is AC, there's two different attributes. Essentially what we are saying is there's a functional dependency from AC to ABC. Essentially AC decides B, right? So some of this functional dependency or constraints, or cardinality constraints expressed in your conceptual model can be actually enforced by the primary key in your logical design. But of course, there could be other constraints, right? I mean, you can only have one primary key for one relation, right? So what if you have two different constraints that you need to enforce, right? We also talk about integrity constraints, right? You can enforce some of this using unique constraint. You can enforce some of them using foreign key constraint, for example. Another thing that we are talking about is once you have this basic design, you also have the flexibility of merging some of these relations together. For example, here you have relation A, like which is a key with attribute A, right? I mean, yeah, so you potentially could merge it together with the relation R, right? Because they all contain the same attributes, right? So you could potentially merge this, and there are so many different ways that you could merge relations together. And for a specific way of merging them, we call them essentially design of your database schema. And for different type of design, you have different property. Some of them will have data redundancy, some of them are going to lose functional dependency. And that is actually what we start to talk about last week. And there's something called database design theory. Essentially, given one application, given so many different ways you can design your schema. What is a good design, right? And what do we mean by a design is good? Because there's so many different things you can measure. right? And how to formally model and enforce the property that we want in a good design. Given a design, how can we reason about its property, right? And how can we say something about its property? And if it doesn't have the property that we want, how can we enforce it? How can we, for example, decompose it into a new design, right? So that actually gave us the property that we want. And that is something that we have been talking about actually from last week, and we are going to continue to talk about it today. So the way to reason about design, I mean, one way to reason about design is by understanding the notion of normal form, right? Essentially, database normalization, right, is a process of essentially structuring a relational database, right, including a series of so-called normal forms in order to reduce data redundancy and also to improve data integrity. And normal forms are essentially common ways that people do to normalize your database system. And for each normal form, there are three fundamental questions that we are really curious about. The first fundamental question is, if you gave me a relational schema R, and if you give me a whole bunch of functional dependencies that you know is going to hold in this application, how can we decide this design, that is R and FD, okay, satisfy a given normal form? That is one thing that we are really curious about. How to check whether functional dependency hold, whether a normal form is satisfied given a design. On the other hand, the second question that we are curious about is that if you give me any schema, R and FD, that satisfy a given normal form, what can we say about it? What is the set of property that it will have? For example, whether we can say, as long as you are in this normal form, you will not have, for example, update anomaly, something like that, right? So what the property can we derive from the fact that this design is in certain normal form? That's the second fundamental question. And the third fundamental question is really, if you give me a relational schema R and a section and a set of functional dependency FD, if it's not in certain normal form, right? How can we generate a new schema R prime such that this new design is actually in the normal form that you want, which can derive the property that you want to enforce in your application? Essentially, for normal form, this is actually what we care about, these three fundamental questions. And there's a whole bunch of normal forms. And toward the end of this lecture, you are going to see a very big table containing a whole bunch of those. But in this course, we are going to focus on 5 of this, okay? And last time we talked about all the way from the first normal form to second to third and to BCNF. If you look at the relationship, they are going to be more restrictive than one another, right? Monotonically. By restrictive, we mean whether they are a law, by restrictive, we mean that if you think about your possible world, if you think about the set of all the possible designs, okay, there are going to be fewer and fewer amount of designs monotonically that satisfy a given normal form, all the way from first normal form to BCNF. They're including fewer and fewer possible designs. That's why we say they are more restrictive in a very precise way. When we talk about first normal form, right, all the way, and today we are going to talk about the fourth normal form, which is going to be even more restrictive than BCNF. But before that, right, let's try to use maybe 10 minutes, just quickly run through all the 4 different normal forms to make sure we can appreciate the first, the first normal form that we are going to talk about today. Essentially, the high-level idea is up to the 4th normal form, we are going to enforce lossless decomposition. Okay, up to 1st normal form, where we're going to stop in this course, is the decomposition itself is going to be lossless. You are going to recover or store exactly the same amount of information, the same information as in your original design. When you go to higher up, okay, so you could actually also lose that property. And another thing is that we talked about last time is up to the 3rd normal form, you are going to preserve all the functional dependencies, all the dependencies. So we already see how you could lose some of the dependency in BCNF, right? It doesn't preserve all the possible functional dependencies. So that is actually the relationship between these 5 different normal forms. But let's quickly run through from 1 to BCNF, right, to make sure we understand what the first normal form really is really talk about. So high level idea behind one normal form to a third normal, first normal form to BCNF is they try to deal with functional dependency. And the first normal form is try to deal with multivital dependency. So what is first normal form? It's very simple, okay? The first normal form essentially says that all the values that you are storing in your database need to be atomic. It cannot be set, it cannot be array, it cannot be list. They need to be atomic values, okay? Pretty much it. So first relation on the upper side is in first normal form because all the values are atomic. You cannot decompose them into smaller element. And the second relation in this case is not in first normal form. If you think about why, because there's a set there, right? I mean, you could implement that into this database. I mean, there's nothing wrong about it. That something is not in first normal form. And whenever you are doing something that's not in first normal form, you have separate learn of theory to help you to reason about its property. So don't worry about that. If you really say, yeah, it doesn't, in your application, if you really say, yeah, it doesn't really make sense to have the first normal form, don't worry about that. There's a whole bunch of theory that you can learn by yourself about how to deal with that. But in this course, the goal is try to teach you how to think about this. It's not how to enumerate all the possible normal forms and make you guys memorize them. It's really try to teach you how to think about normal form. Why do we have normal form, and how can we develop the theory behind it? And then to make sure when you want to define something new, you can do that all by yourself. Okay. So the first one is first normal form. The second one is not. And the second normal form, right? So it's essentially try to get rid of some of the redundancy that we have in our data. So here's the motivating example, right? You have essentially multiple functional dependencies, but some of the functional dependency, in this case, the student ID to the student name, right? So have the left-hand side, right? The student ID as part of the key, right? So because whenever you're talking about a primary key, you could have, if the primary key contains multiple attributes, you could have duplicate information for one of those attributes, right? For example, here the primary key is student ID and lecture number, right? Yeah, the same lecture number could appear multiple times because your primary key is a set. In that case, if that attribute that could appear multiple times also decide some other attributes, then you have duplicated information, right? So which is pretty reasonable to think about. The goal of the second normal form is really try to get rid of all those data redundancies. Essentially, it says that if you give me a design, a set of functional dependency FD, it is in second normal form, if and only if that every non-key attribute, every attribute that is not part of any key, every non-key attribute is minimally dependent on every key. By minimal dependent, we mean there doesn't exist another functional dependency that decides this non-key attribute, but the left-hand side is part of a key, is a subset of a key. So clearly from this example, right, that from this definition, the example from the right-hand side, we see this design, right, is not really in second normal form because you have the student ID, decide name and semester, and but the student ID on the left-hand side is only a subset of the key. And then we go even beyond second normal form in terms of getting rid of data redundancy. We have another normal form called the third normal form, right? Which gets a little bit more complex. It tries to get rid of more redundancy. It essentially says that if you have a design that's in third normal form, it means the following. That is, if you check all the functional dependencies that you have in your system from alpha to B, okay? So at least one of these following conditions need to hold. Either this functional dependency is trivial, okay? That is, you have the right-hand side B as a subset, it's one element belongs to alpha, okay? Belongs to the left-hand side, right? So this is natural because this is something that out of your control, right? So the moment you have a relation with more than one attributes, you are going to have some functional dependencies, right? No matter how you design the system, they will be there because they are trivial functional dependencies that always hold, right? In this case, if you have the right-hand side is a subset of the left-hand side, oh, that functional dependency will always hold. There's nothing you can do about it. So this is reasonable, okay? And second condition is that B is the right-hand side is an attribute of at least one key, okay? And the third condition is alpha is a super key of R. That is alpha is a superset of some keys, okay? So the intuition behind it, if you think about second condition and third condition, is if you have a functional dependency that does not satisfy the second and the third. So intuitively, this alpha, right, is more or less a concept in its own, right? We probably want to have a separate table, right, to have this alpha there, like instead of having this alpha in this original table. And another thing that Sternal form try to get rid of is all those transitive dependency type of thing, right? You have A decides B, you have B decides C, right? Whenever you have this, you start to have redundancies because from A decided B, the B can appear multiple times inside your database, right? So, and you want to get rid of that by saying, yeah, I will define some normal form such that in this case, B decides C is going to be the evil functional dependency that we need to get rid of from the design if you want to be in Sternal form. Okay, so and it's very easy to see the thing on the right-hand side is not really in Sternal form. And Sternal form doesn't get rid of all the data redundancy caused by functional dependency. So there's another one called BCNF that's even more restrictive. So essentially it says if a design is in BCNF, if and only if for all the functional dependencies that you have in your system, it satisfies at least one of these two conditions. Either it's trivial, there's nothing we can do about it. The second is alpha is a super key of R. Essentially get rid of the second condition in Sternal form. So essentially intuitively, this pretty much means in each relation, you only store the same information once, right? So the thing on the right-hand side is in Sternal form, but actually not in BCNF, right? Because it also have some data redundancy caused by functional dependency. So there's one question. In BCNF, why is D not a super key of R since it is a candidate key? So in this case, a very good question. D is not a super key of R because D is not a candidate key, right? So what is a candidate key? Candidate key means that if you take that candidate key, which is a set of attributes, you can decide all the other attributes, right? So in this case, D decides C, but D doesn't decide A and B. Right, so essentially D is part of candidate key, right? AD is the candidate key, D is a part of it, but D is not a superset of that. D is a subset, D is a subset of it, right? So perfect. Okay, so if you have any questions, raise your hand or just put your question in the chat window. Okay, perfect. Now we have this BCNF, we have this Sternal form, right? So there are multiple things that we talk about. So how to turn a database into a BCNF, how to turn database into a Sternal form, and why do we even need like these two different normal forms, right? So and for the Sternal form, for BCNF, we talk about the decomposition algorithm, right? Which we are not going to detail today. Essentially, you try to find, you try to check whether it's in BCNF or not. If not, it must, because you have some evil functional dependency and you decompose it. Okay, according to that functional dependency, you continue to do this, you are going to have something that's in BCNF. So, and then for Sternal form, right? So there's also an algorithm to turn design into Sternal form. It's actually go the other way around. Essentially, what you are going to do is you compute the basis of functional dependency, right? And then that's a minimal collection of functional dependency that you need to describe the original collection of constraints. That's what basis really means, right? And we talked about how to compute the basis last week. You compute the basis for every single rule, functional dependency in the basis, you create a relation. And then if there's no key, you create another relation and you merge if one relation is a superset of the other one. That's it, okay? So again, like it sounds very simple, but it really needs some practice, okay? Read the textbook, go through some of the example there by yourself, And then it should be very easy to understand. But it's very hard to understand if you do not do the practice all by yourself, because it's pretty abstract. But once you actually have done that once, yes, like reading a bicycle is very hard to forget. Okay. And we also talk about how to put BCNF and Sternal form essentially side by side to understand their property. What's interesting is that if you look at Sternal form, it actually tries to emphasize correctness in the sense that all the functional dependencies will be preserved. But on the other hand, it could contain data redundancy caused by functional dependency. And if you look at the BCNF, right? So it's trying to emphasize efficiency. That is, it doesn't really have data redundancy caused by functional dependency. It could have other data redundancy, which I'm going to talk about today, but it doesn't have data redundancy caused by functional dependency. But the downside of that, there's no free lunch, right? The downside of that is that it could lose functional dependencies, okay? So that's actually the trade-off. In your application, depending on what you want, if you are doing Sternal form, you are going to have correctness for free, but the downside is that at the application layer, okay, you as a user need to deal with all those anomalies caused by data redundancy. For BCNF, right? So you are going to have a really good kind of like data redundancy property. But on the other hand, as a user, you need to handle all the functional dependencies that actually being lost during the translation, right? If they are really important to you. So there's like no universally better solution between BCNF and Sternal form. Whichever makes sense depends actually on your application. So this is a normal form all the way from first normal form to BCNF. And then let's talk about the different normal form that even more restrictive than BCNF, which actually is inspired by this example, right? So if you look at this example, right? So here you have 3 different attributes, and the value of B and C, right, are actually conditional independent on the value of A, right? Given the value of A, right, whether whenever you have the tuple B and BB, right, it doesn't matter what value of C is. You have the value C and CC, right? Each one will have 2 different combinations, like 2 different potential values, and then you have 4 different tuples, right? In this case, the value of B and C are essentially independent, like to each other. Once, like whenever you have this property, right, we can see, okay, there's no functional dependency here, right? I mean, given A, I cannot decide B, I cannot decide C, right? There's no functional dependency. However, there are data redundancy, right? Because clearly I'm storing the information that B appears twice for A, right? So I'm storing that twice, right? So clearly there are data redundancy caused by things that it's not functional dependency. And that's actually going to inspire what we are going to talk about today, which is essentially something we call multivital dependency. We started a little bit last week, but let's try to refresh our memory. Essentially, at the high level, right, it's try to encode information that some value, for example, B, have no impact on the value of C, condition on A. Formally, if we say there's a multivital dependency from alpha to beta, for the relational schema contains 3 subset attributes, alpha, beta, gamma, if and only if the following is hold. That is, for any pair T1 and T2 in R, if they match on alpha, if they share the same value on alpha, it implies the following: that you are able to find T3 and T4, another 2 tuples, could be the same tuple, to be honest. And you are able to find another 2 tuples, could be the same tuple, such that they all match on alpha. But T3 takes the beta from T1, T4 takes the beta from T2, but T3 takes the gamma from T2, different one, and T4 takes the gamma from T1. So this is a very precise way for us to say, yeah, it doesn't matter. This is actually very precise way to say, yeah, the value of B and C condition on A, because they all need to match on alpha, doesn't really matter. You can, for any 2 tuples sharing A, you can swap them, beta and gamma, find a new pair of tuples that also in my database. So that is actually precisely what we are trying to say about something that doesn't really matter. Intuitively, right, when you have this database instance, right, T1 and T2 have their own beta and gamma value, essentially this condition pretty much means I can also find T3 and T4 if there's multivital dependency from alpha to beta. Okay, I can swap them and it's still in my database. So it doesn't really matter. And for this example, right, it's very easy to see there's a multivital dependency from personnel number to language. There's multivital dependency from personnel number to programming. So again, it's also pretty easy to see that multivital dependency can result in anomalies and redundancy, right? So that is why we need to think about how to get rid of them. So the different view looking at the multivital dependency is by looking at it via the lens of lossless decomposition. So essentially, if you have a multivital dependency from alpha to beta, so here from personnel number to language, for example, so you can actually decompose this R losslessly by just do the projection, keeping alpha and beta have one relation, and keep alpha and gamma, right, as another relation. And if you join them together, you are going to get the same thing, which is pretty easy to see from the example from the right-hand side, right? You could decompose it into two relations. One contains personnel number and language, another contains personnel number and programming, right? Because it doesn't really matter. Once you do the natural join on personnel number, you are going to essentially recover like essentially the same thing, okay? So in fact, right, so the decomposition of R into R1, R2 is lossless, right? So if the following hold, that you have multivital dependency from alpha to beta, and you have multivital dependency from alpha to gamma. Okay, so this is something that we already know, right? So it's a very quick run through like about last week. Now, similar to functional dependency, we can also reason about multivital dependencies, right? And here we are going to actually talk about how to do it. So first one, there's a whole bunch of trivial multivital dependencies. In this case, if you have relation R and theta, okay, there's a one trivial function multivital dependency from alpha to alpha theta. Okay, so essentially another way of writing this is if R is a full set of attributes that you have this functional dependency from alpha to R. Okay, so yeah, sorry, just give me a minute. Yeah, sorry. Yeah, so like you have this trivial multivital dependency, right, from alpha to R that decides essentially like when we talk about something being trivial, this is what we mean, right? So as you can see, this is also the same as what we have for functional dependencies. So how can we prove it, right? So that's something that let's think about that together. So similar to functional dependency, I mean, it's a good way to actually prove it. Is actually to go back to definition. What do we even mean by this, right? So what do we mean by alpha have multiple dependency between from alpha to alpha theta? Essentially, we want to prove the following. That is, for all pairs of tuples T1 and T2, as long as they match on alpha, it implies the following. That is, we can find T3 and T4, that these four different tuples, they share their value on alpha. But on the other hand, right, so T3 and T1 going to share alpha theta, T4 and T2 going to share alpha theta. And because you are talking about R being the full side, right, so the gamma side is going to be empty side, right? So you all have alpha, beta, gamma in definition, but the gamma here is going to be empty side because beta is going to be a full side, right? So how can we find such a T3 and T4? Right, so the game of playing like proving multiple dependency laws pretty much is try to find all the T3 and T4 given T1 and T2. It's very easy, right? In this case, you can just set T3 equals to T1 and T4 equal to T2, then you're done, right? So you can say, yeah, so if you give me T1 and T2, I can always find your T3 and T4. that T1 is the same as T3 is the same as T1, T4 same as T2. Once I do this, right, T3 is alpha theta going to be same as T1's alpha theta because they're the same tuple, right? And T4's alpha theta going to be same as T2 alpha theta because they're the same tuple. Of course, they share the same alpha, and they match on the empty side because there's no value there, right? So this is a very simple proof about this functional dependency. Right? As you can see, this is something that you don't really have too much control in your design. Once you have a design with multiple attributes in a relation, right? So yeah, you have a whole bunch of multivital dependencies that are trivial. You cannot get rid of all of those because no matter what you do, the trivial thing will be there. Okay. So similarly, right, you have something like this, right? Because the symmetric structure in the definition, right? If you have a relation like alpha and theta, you always have something like you have MVD from alpha to theta. Okay, so that's also something that is very easy to prove. Yeah. So there are actually more laws about functional dependency. There's another case that's trivial. That is, assuming I have two collection of attributes, alpha and beta. Okay, so and the beta is a subset of alpha. In this case, you always have the multivital dependency from alpha to beta. Okay, so essentially a superset is going to multivital decide in the multivital case beta like a subset. So how can you prove that? Yes, let's go back to definition, right? So if you want to prove there's a multivital dependency from alpha to beta, what do you do? Essentially, you are trying to prove for all pairs T1 and T2, if they share value on alpha, it implies that you can find T3 and T4 such that they share on the same alpha. It's always like that. And T3 share beta with T1, T4 share beta with T2, T3 with share gamma with T2, T4 share gamma with T1. This is the definition, right? So in this case, if you set T3 equals to T2 and T4 equals to T1, you pretty much get what you need. Why? Because beta is a subset of alpha. No matter how you pick T3 and T4, right? So like because they all share value on alpha, no matter how you pick T3 and T4, they will share the value on beta because beta is a subset. In this case, essentially, you do not need to enforce the second condition about beta because they always hold, because beta is a subset of alpha. Then all you need to do is, okay, you want T3 to share gamma value with T2, then how about I just set T3 equal to T2? You want T4 to share gamma value as T1, let's set T4 equal to T1, right? Once you do that, that's your T3 and T4, given this T1 and T2. So that's it, okay? So it's a very easy way to actually prove this trivial functional dependency, okay? So far, so good, right? Again, if you have any questions, raise your hand or type some question in the chat window, I will answer them, okay? So there are more interesting rules about functional dependencies, fortunately. There's one rule called promotion, right? Which essentially says the following. If there's a functional dependency from alpha to beta, alpha decides beta, then it implies there's a multivital dependency from alpha to beta too. Essentially, the moment you have functional dependency, you have multivital dependency. So how can we prove this? This is actually very interesting. So proof's not that hard. So again, you go back to definition. What do we mean by there's multivital dependency from alpha to beta? Essentially, you are seeing the following. Again, I think we have been looking at this multiple times now, right? So you have T1 and T2, you try to find T3 and T4, satisfying this condition. So because we have the function dependency from alpha to beta, we know that if all these tuples sharing value on alpha, it implies they will also sharing the value on beta, right? So right. So there's no magic about it, right? So this is what functional dependency really means. And because of that, you have a very similar proof as in the previous case that you have the subset. Because that's also the same, right? Once I match on the superset, yeah, my value on the subset will be the same. Here, essentially, you are saying, yeah, once I match on alpha, I also match on beta because there's a functional dependency. They don't have the same structure. You take the same value, then you are done. Okay, so look kind of different, definitely longer proof compared with the trivial multivital dependency. But the intuition is the same. Because you have this function dependency define the value between relationship between alpha and beta. If alpha match, beta will match. That can be caused by multiple reasons. It could be caused by functional dependency in this case. It also could be caused by the fact that alpha is a superset of beta, right? But whatever it is, it's the same type of proof. So you have this promotion rule. That is, all the functional dependency can be promoted to multivital dependency, and that's true. Okay. So is the other way around correct? Do we have the other way around? That is, if you have a multivital dependency from alpha to beta, can we say there's a functional dependency from alpha to beta? So first of all, it's easy to guess, probably no, right? Otherwise, they'll be equivalent, right? So, but let's also try to reason about it in a more precise way. Essentially, the answer is no, right? So, and this is the concrete example, right? So essentially here, right, you have the multivital dependency from personnel number to language, from personnel number to programming. There's two different functional dependencies, two multivital dependency, but clearly there's no functional dependency from personnel number to language. There's no functional dependency from personnel number to programming, right? Because given the same personnel number, you cannot decide a unique language. There are two of those, right? For 3002, you cannot decide the programming. There are also two of them for 3002. So there's a MVD, but there's no FD, okay? So that's the other way around of the promotion rule, which is not true, okay? And then there are actually other more interesting rules. For example, here's one rule that's kind of interesting. That is, if I have a multivital dependency from alpha to beta, then that implies I have the multivital dependency from alpha to the complement, that is to R minus alpha minus beta. Okay, so looking at this concrete example, right, essentially it says if you have a multivital dependency from personnel number to language, that implies that you will have a multivital dependency from personnel number also to programming. Okay, so the proof is actually very simple because if you look at the definition, it's actually symmetric, right? So you have alpha, beta, and gamma. You define multivital dependency to alpha and beta. You can actually swipe the gamma in the definition, get the same thing, right? So the definition is symmetric, and that is why you have like this symmetric structure. We'll talk about this two multivital dependencies. Both will hold. If one hold, the other one will also hold. Okay. And then there's another rule called the multivital augmentation, which look like this. It's very similar to the functional dependencies, right? But essentially you have a multivital dependency from alpha to beta, and you have two collection of attributes, delta and gamma. The delta is a subset of gamma. So you can actually put the gamma on the left hand side and delta on the right hand side. Okay. Essentially, alpha beta going to have multivital dependency from alpha to beta and delta. Okay, so you put the superside on the left hand side, which I think makes sense, right? Because we have that like a trivial functional dependency, saying that superside going to decide a subset. You put the larger one to the left hand side. You put the smaller one to the right hand side, and you still have that multivital dependency. The proof, your homework, it shouldn't be that hard, okay? And then there's another rule called multivital transitivity, which is kind of interesting. Now we are going to look at how to prove it together. Essentially, you have two multivital dependencies in your system. You have the MVD from alpha to beta, you have MVD from beta to gamma. So the multivital transitivity rule essentially says that once you have these two multivital dependencies, it will imply you have another one, which is from alpha to gamma. How can we prove this? This is actually pretty interesting. So let's look at this very quick proof sketch together, because it's kind of go to the core about how you prove those multivital dependency rules. Again, you go back to the definition, right? So what do we need to do to prove there's an MVD from alpha to gamma? Well, the thing you do is you say, yeah, so this is my T1 and T2. They share the same alpha, all of the A, and they are very different for the rest of the attributes. One is BCD, another B prime, C prime, D prime. And you say, yeah, I can always find T3 and T4. Okay. How can you do that? Yeah, you say, yeah, here's T1 and T2 because I know there's an MVD from alpha to beta, right? I can apply that. Then I say, yeah, S1, S2 must be in the system because I have MVD from alpha to beta. And what does alpha beta try to tell you? It try to flip, right? It try to say, okay, so S1 take the same value, same B value from T1, S2 take the same B value from beta value from T2, so have B and B prime, and then I swap the rest of it. Then S1 has C prime and D prime, and S2 have C and D. So these two must in the system. And they'll say, okay, now I know S1 and T1 must be in my system. I apply the second function multiple dependency on T1 and S1. And then I will take those. They share the same A and B, right? As you can see, they share the same A and B. And then I swipe the C and D. Okay. And then you have this S3 and S4 and S5. You say, yeah, if T1, T2 is in the system, then I know S1, S2 is in the system. Then I know S4 and S5 is in the system. And then you apply your function your multiple dependency, this one to another tuple S2 and T2. Then you get these two tuples. Okay, you say, yeah, because of T1 and T2 is here, all of the 6 tuples must be in my system. And then you set T3 equals to S7, T4 equals to S5, then QED. Okay, then you find the tuple you want to find to prove there's a multiple dependency from alpha to gamma. Okay, so when you go back home, try to read this proof. It's very simple. The game is very simple. You just try to find those pair of tuples that give you the T3 and T4 in the definition. Okay, so that's the first half of the lecture. Let's take a break, and when we get back, we are going to continue talk about multiple dependency. And in the meantime, if you have any questions, I'll be here to answer them. You can just unmute yourself and ask the question, or you can just put them in the chat window. Okay. Yeah. Okay, so let's continue. So now we know how to reason about like those multivital dependency stuff, right? So there's a trivial multivital dependency, and then there are multiple dependencies that you can actually derive if you know some of the multivital dependencies. So there's one thing that kind of we need to kind of be careful about. That is when we talk about functional dependency, right? We talk about the Armstrong's axiom, right? That's three beautiful, simple axioms that are going to derive all the possible functional dependencies, right? So, and we also talk about a whole bunch of rules that we can apply to functional dependency. When you talk about the multivital dependency, it's very important to actually keep in mind that not all of the functional dependency rules going to apply to multivital dependency. So you need to be careful. Some of the rule looks very natural, right, in the context of functional dependency, but going to be very different in the context of multivital dependency, which is actually an analogy will be there's a lot of when we talk about the set semantic and the back semantic of algebra, right? So there are a lot of rules that looks very natural when you think about two things, sites, right? But when you say there are multi-sites, they're going to have different collection of rules, right? So just look at one example, right? So you have this functional dependency, right? Which is actually like a very trivial rule, right? You have alpha decide beta and gamma. That's going to imply alpha decide beta and alpha decide gamma, right? So from functional dependency, that makes sense. But on the other hand, we'll talk about a multivital dependency. This rule doesn't really hold. You cannot decouple the right-hand side, okay? So, I mean, just a very simple counterexample, right? So in this case, you have the multivital dependency from language to the combination of personnel number and programming, right? Why? Because the trivial one, right? So we talk about this, right? One attribute have multiple dependency from that to the whole set, to the rest of the tuples, right? Sorry, like rest of the attributes. So this is a trivial multivital dependency. But on the other hand, clearly you cannot decouple them, right? You cannot say, because I know there's a MVD from language to personnel number and programming, then I have the multivital dependency from language to personnel number or language to programming. Clearly that doesn't hold, right? So this is just one counterexample about this rule. So essentially, when you are trying to reason about multivital dependency, try to be careful and not all the rules that look very natural. For example, for this rule, right? So alpha to beta gamma imply alpha to beta and alpha to gamma. It looks very natural, but it doesn't always hold. Okay, so really be careful when you reason about multivital dependencies. So now this is all about multivital dependency. As you can see, it's introduced different ways for you to talk about data redundancy, right? So how can we get rid of this? How can we reason about the data redundancy caused by multivital dependency? And that gave us something called the forced normal form, which is even more restrictive than BCNF. So we say a design R is in forced normal form if and only if the following hold. That is, for all multivital dependencies you have, at least one of the following two conditions need to hold. Either this multivital dependency is trivial, right? Nothing you can do about it. Or alpha, the left-hand side, is a super key of R. Okay, so if you look at this, it's very similar to BCNF, but here we are trying to enforce this not only for all the functional dependencies, as in BCNF, but also for all the multivital dependencies. So that's the difference. So one thing that we can say is if you have a design that's in forced normal form, that's going to imply this design is also in BCNF. Okay, so essentially forced normal form is going to be more restrictive than BCNF. How we improve that? Right. So let's try to think about how can we prove this together, right? So what do we want to prove? We want to say, if R is in forced normal form, then R is in BCNF. One thing we could do is we can prove the other way around. We can say, so assuming like R is not in BCNF, that implies R is not in forced normal form. We do the other way around. And once you do this, right? On the left-hand side, we know, okay, R is not in BCNF. That means you must be able to find a non-trivial evil functional dependency that make it not in BCNF, right? Otherwise, it's in BCNF. So there's at least one of these. I call it alpha to beta, alpha decided beta. And then promotion, you say, yeah, I know, it's alpha to beta. Then that implies there's a multiple dependency from alpha to beta too. And if you look at this alpha to beta, right? So for multiple dependency, clearly is a non-trivial evil multiple dependency for first normal form, right? Because the condition between these two are almost the same between BCNF and first normal form. If one functional dependency is evil for BCNF, then its multi-value promotion is also going to be evil for first normal form. And then QED, and they are done, right? So clearly this R will also not be in first normal form. That's actually one way to prove that if a design is first normal form, right, it's implied it's going to be in BCNF. So the diagram that we show in the beginning of this lecture is actually correct, right? First normal form is actually more restrictive than BCNF. Another question is, given the schema does not in first normal form, what can we do, right? So similar to BCNF, you also have the decomposition algorithm for first normal form. So here you input the schema, and your output will be R1 to Rn, smaller relations, such that this is a lossless decomposition of R. If you join back R1 to Rn in a predefined order that you define, okay, you are going to recover the original information. You are not going to lose tuples. You are not going to introduce more tuples, okay? And the second is R1 to Rn are going to be in first normal form. So how can you do that? It's very similar to BCNF, right? You start from your original relation in your result set. And then you say, yeah, so let's try to check whether every single relation in this result set is in first normal form or not. If they are in first normal form, then I'm done. Then I have this collection of relations and return. If it doesn't, then there must exist a relation Ri such that it's not in first normal form. And that implies there must be an evil multivital dependency from alpha to beta, for example. And then what I do is going to decompose it. I'm going to keep alpha and beta, project them into a different relation that's called R1. I'm going to take the rest of the tuple. I'm going to take Ri minus beta. I'm going to keep alpha because I need something there to join between these two relations. I'm going to keep alpha, the left-hand side. We're going to get rid of beta. Okay. Then I have a new relation R2. Then I put this into the result side, get rid of the original Ri. I continue to do this until the whole thing is in first normal form. So last time we talked about, yeah, so this one will always terminate, right? So the same argument will apply here because every single time you decompose it, if you count the amount of evil MVD, that number is going to decrease by 1 at least, okay? And then because you have a finite amount of evil MVD in the beginning, right? This algorithm will always terminate. And once it's terminated, it will have a design that's in first normal form because otherwise it won't terminate. And it's going to be a lossless decomposition because you can prove by induction. Every single time I decompose it, it's lossless, right? So then I can just prove the whole thing is lossless by doing induction. So this is the decomposition algorithm. And it's actually pretty natural if you think about it. What's interesting if you can put this BCNF and the first normal form essentially side by side, okay? Now let's look at this example. Now you have this multiple piece of information put together. You have the professor table, contains the personnel numbers, the name, the area, the advisor, for example, right? And then you have the language the professor speaks and the program language the professor can use. Okay? Assuming you have this relation. And assuming we have 4 actually very natural type of dependencies. you have the functional dependency saying that, okay, in this application, the personnel number are going to decide the name, area, advisor, of the professor. And the second thing is, you are saying that the personnel number and language and programming language is the key. It's going to decide the rest of the attributes. Okay, personnel number, language, programming, decide name, area, advisor. Right, essentially this is the key. Well, at least one candidate key, one key. So these are the two functional dependencies you have in the system, which is very natural if you think about it. And then you have two other multivital dependencies. You have one multivital dependency from personnel number to language. Okay, and then you have another multivital dependency from personnel number to programming. Okay, so once you have this 4 different dependency rules, you can actually run the decomposition algorithm for BCNF and for forced normal form. If you run that for BCNF, what are you going to have? Yeah, I mean, for this one, the only evil functional dependency here is the one from personnel number to name, area, advisor, right? So, and then you're going to decompose it. You are going to create 2 relations. The first one contains personnel number, name, area, advisor. The second one going to contain personnel number, language, and the programming. And then you are done. You cannot decompose anymore because there's no non-trivial functional dependency for this second relation, right? So, and then if you are going to do forced normal form, what are you going to have, right? First one, because of promotion rule, every single functional dependency here is going to become multivital dependency, right? So if you have this evil functional dependency from personnel number to name to area to advisor, for example, that is evil for BCNF, its multivital promotion is also going to be evil for forced normal form. So you could still like decouple it, right? You can generate one relation with personnel number, name, and area advisor, and you have another relation with personnel number, language, and programming. And then if you look at this personnel number, language, and programming, you'll say, yeah, it also does not enforce normal form because I have an evil function, multivital dependency from personnel number to language, from personnel number to programming, for example. So then what you are going to do is going to, okay, I can also decompose it again, right? You can decompose this one into these 2 smaller relations. One contains personnel number and language, another contains personnel number and programming, right? If you put it side by side, as you can see, the forced normal form is going to give you strictly like, okay, so if you decide the same order of decomposition, it's going to give you strictly smaller relations, okay? That's going to get rid of more and more redundancy compared with BCNF. Essentially, BCNF is going to get rid of all the data redundancy caused by functional dependency. Forced normal form is going to get rid of all the data redundancy caused by functional dependency and multivital dependency. So forced normal form is going to get rid of even more data redundancy. The downside, it could actually lose more functional dependencies. It could even lose some of the multivital dependencies, right? If you like during the decomposition. Right? So the same trade-off also hold. There is a fundamental trade-off between correctness, which is how many dependencies, both functional and multivital, that you can preserve in your design. And then there is the efficiency, right? How much data redundancy that you are going to allow in your design. So that fundamental trade-off will not change, even if you have the first normal form. And in practice, right? So we talk about these 5 different normal forms. In practice, there's a whole bunch of those, and people continue to do this. Like even in like 2012, people still have, here's a new type of normal form, right? So there's a whole bunch of those. People have been doing this in the last literally like 50 years. And for each one of them, you see there's a different properties, right? That you can say about each of these normal form. And that's the beauty of it, right? Once you know a certain design is in some normal form, automatically there's a collection of properties that you can actually immediately say about it. For all the possible database instance, you can fit into that schema. It must have this property. So that is actually the beauty of it. So when we talk about normal form and ER modeling, right? So essentially, remember, we talked about one rule like 2 weeks ago about how to translate entity relationship diagram to relational model. And that algorithm automatically going to give you something in third normal form. Just refresh our memory about that rule, right? Entity sets become relations, okay, in the ER diagram. Relationships in the ER diagram going to become relations. And then you try to merge relations with the same key, okay? So if you follow this rule, do the translation from ER diagram to a relational model, you are going to at least get third normal form, okay? The reason behind it is all the functional dependencies in your system in the ER diagram, they are actually caused by kinetic constraints from relationships, right? So that's the only functional dependency that we introduced. So once you do this, you are going to have a third normal form at least. If you want more, you can run the decomposition algorithm to give you BCF, or can run more to give you essentially like fourth normal form, okay? And here we talk about normalization, right? So one thing that we need to be really careful about is whether normalization is higher the better, right? Is BCF always better than third normal form? Is fourth normal form always better than third normal form? Something like that. No, right? So there's always a trade-off, like many things in computer system. So in practice, right? So people actually want to do denormalization, like just normalization, the process that you go from a lower one to a higher one, right? So in practice, people actually want to do denormalization for many applications because it also provides benefits, right? For example, if you look at this very big table, right, contains a whole bunch of information. I mean, it have a whole bunch of data redundancy, but on the other hand, it's also very fast to read, right? Every single time you read a tuple, you get a whole bunch of information there, right? If you separate them to a whole bunch of smaller relations, if your application always use this big tuple, every single time you fetch information, you need to join those relations together. Very hard to write a query, but also very hard for the system to actually run that for you, right? Denormalization in practice could give you a whole bunch of benefit, and in practice, people actually do that all the time. Okay, they're going to denormalize up to a case that data redundancy will not cause a problem, but read can be faster. Okay. So on the downside, of course, right? So there could be data redundancy caused by normalization, right? So when you normalize that to higher, right, it's easier to maintain consistency, right? If you just put the two schemas side by side, right? It also depends on whether your workload is read only or not. Okay, so in practice, there are workloads, actually a lot of workloads, that all you are going to do is to try to read about stuff. You are not going to update your information. So if that's the case, right, so just introduce another factor into your decision about whether to normalize or whether to denormalize, right? Because there you don't really need to maintain consistency because data will never change. All I'm doing is keep reading, right? So I'm just going to like give you like essentially very different answer to the final design. Again, like in practice, right? Here we talk about normal form. There's nothing wrong about not being normal, right? So you do whatever makes sense, like in your applications, right? So again, the goal is really try to teach you the way to think about it, not to give you an exclusive list of design that you must use, like in practice. Okay, so that's actually all for today, right? So we didn't use up the whole 90 minutes because this is actually the last chunk of the first segment of the course. I will be here for however long until there's no questions anymore. And whatever question you guys have, you can just unmute yourself and I will be here to answer them. Yeah, thank you guys very much. And on Friday, we are going to do our first exam review to actually refresh our memory, put the structure into what we've been talking about. And we are going to also do some exam questions together. Okay. Yeah. So I see you guys on Friday. Yeah. In the meantime, if you have any questions, just let me know. Yeah. You can unmute yourself and ask. Oh, there's a very good question from the chat. Essentially, I said functional dependency in ER model are only caused by kinetic constraints from the relationships. What about the keys from the unity? Oh, yes, the keys from unity we also give you functional dependency. Sorry, yeah, I was wrong. Yeah, let me update it. Yeah. Okay, so there's one question that is, what is the intuition behind MVD, right? So essentially for MVD, right? So like look at like this example, right? So if you look at this, right? What you're going to have is like this person, right? 3002. This person can speak two languages, Greek and Latin, and can program in two languages, right? C and Pascal. If you look at this B and the language and program language, they are independent, right? So like whether there's no strong correlation about this two, right? Essentially, when you have two languages that someone can speak, you'll have three program language, you'll end up have four different tuples like in this relation, right? And that's the data redundancy that we are trying to get rid of, right? We want to say, yeah, let's define something that to say there's a multiple dependency from personnel number to language to actually encode kind of the information that given the person, the choice of the language is independent from the program language. When you have n language and m program language, I am going to have n times n tuples. Make sense? Answer your question? Yeah, perfect. Yeah, so if you have a question about other things, like all the previous lectures, right? So like here, yeah, I'm here to answer. Yeah, keep typing things in the chat window and unmute yourself if you want. So yeah. Yeah, so one question in exercise 4, the one is pandas data frame exam relevant. Yes, it is exam relevant, but it will be relatively simple. We will not go deep into Python or those type of things. That's not relevant. But how to do those relational algebra thing in pandas data frame is, yeah. Pretty much that function calls, right? So we do not assume you know Python. Yeah. But we assume you know how to do function calls and do joins, for example, in pandas, right? Oh, what is LH? Oh, sorry, yeah. LH as left-hand side. Okay, so if there's no other questions, I'll see you guys on Friday. So like again on Friday, I will also stay on the Zoom call like longer after the lecture, and whatever question you guys have, just you can also ask on Friday. Okay, yeah. See you guys on Friday then.